Hello everyone. In this video, let us see the concept of hybridization. In order to overcome the drawbacks of valence bond theory, there are few drawbacks in explaining the bonding in beryllium chloride. If you look at beryllium chloride, according to valence bond theory, this should not form covalent bond, because in beryllium there are no unpaired electrons. There are no unpaired electrons. Here the valence electrons are paired up. According to valence bond theory, unpaired valence electrons only will participate in the bonding. But so according to that, this should not participate in the bonding. But still it is forming covalent bond. That means two covalent bonds with two chlorine atoms. So in order to explain that, Linnaeus, the same scientist who proposed the valence bond theory, has proposed the concept of hybridization. Drawbacks, he has proposed the concept of hybridization. According to this hybridization, these valence electrons present in the valence atomic orbitals are going to intermix and they are going to redistribute among themselves to form equal energetic atomic orbitals, which are equal in shape and also in the energy. So that the atomic orbitals of almost similar energy. That means they will be having almost similar energy, but not a very great difference in energy. See, if it is 2s and next is 2p, the energy difference will be very less. These two atomic orbitals will undergo intermixing and they will be redistributed to form an equal energetic atomic orbitals. That redistribution is known as what? Hybridization. So this, if you take atomic orbitals, let us take this as 2s atomic orbital. Let us think this is energy profile. This is 2s atomic orbital and this is 2p atomic orbital. These two atomic orbitals are going to intermix and they are going to redistribute among themselves to form what? To form similar energetic orbitals. These similar energetic orbitals are having same shape and also same energy. These orbitals are known as what? Hybridized orbitals. Right. So that phenomenon is known as what? Hybridization. The intermixing of atomic orbitals, almost equal energetic atomic orbitals, to form similar energetic and similar shape containing orbitals are known as what? Hybridization. Right. These will be distributed in the space such that they will face minimum repulsion and they will occupy maximum space. They will be having maximum space between the atomic orbitals. Now let us try to explain this beryllium chloride. Right. So beryllium chloride, Z of beryllium, atomic number of beryllium is 4 with 1s2, 2s2 electronic configuration, and in the first excitation, you know what is excitation? The electrons present in a particular orbital will jump into the next atomic orbitals. This is known as what? Excitation. Here the two electrons are paired up. One of the electrons from 2s orbital will jump into 2p orbitals and they will be occupying that particular orbital. And they will be having one unpaired electron. So in the first excitation, what happens? 1s2, this is inner orbital, and 2s1. By the excitation, what happens? One of the electron will enter into 2p. 2s1, 2p1. And this 2p is also of x. You know that this is having 2px, 2py and 2pz. So the electron will enter into 2px orbital. So right, by this what happens? Two atomic orbitals will be formed. One is two atomic orbitals with one unpaired electron. This is 2s and 2p. These two are going to intermix and they are going to form 2s, 2p are there, they are going to intermix and they are going to form two equal energy rings. Here there is a difference in the energy, right? This is low energy ring and this is high energy ring. So that they are going to intermix and redistribute to form equal energy ring. sp hybridized orbitals. And where do they come from? One is from 2s and other is 2px1. 2s1, 2px1. These 2s and 2p electrons will be now pairing with two chlorines. You know that chlorine will be having the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. One unpaired electron will be present in this is 3px, this is 3py, this is 3pz. So this one unpaired electron present in the 3pz atomic orbital will be pairing up with these hybridized orbitals. Like see here, these and these are going to overlap and they are going to form bond. Before that, what happens? These two atomic orbitals which are present around, that means the hybridized atomic orbitals of beryllium are going to distribute in such a way that there is minimum repulsion between them. There is minimum repulsion between these two. These two are what? sp hybridized orbitals, such that there is 180 degrees of separation between them. Now these two chlorines with their 3p orbital, 3pz, this is what? 3pz1 orbital are going to overlap with these beryllium's sp hybridized orbital and they are going to form a covalent bond like this. This is a 3pz atomic orbital of another chlorine. This is a 3pz atomic orbital of first chlorine, and they leads to the formation of covalent bond like this. What is this bond now? 3pz sp bond. 3pz sp 3pz overlapping. 3pz sp 3pz overlapping, which leads to the formation of two covalent bonds. Right, as these are similar in energy and similar in shape, the resultant bonds will also be with the same properties, that is same size and same shape. Right, now let us see the next example of boron trifluoride. Right, you know boron with atomic number 5 and electronic configuration 2p, 1s2, 2s2, 2p, 1. What happens? This first excitation, you know what happens here? 3 unpaired electrons are required because it is going to form 3 bonds with 3 fluorines. So how many unpaired electrons are required? 3. But how many unpaired electrons are there? There is only one unpaired electron in the 2p atomic orbital. So what happens? They undergo the first excitation, and in this first excitation, what happens? This electron from 2s orbital will jump into 2py atomic orbital. This is 2s, this is 2px, and this is 2py. Due to this excitation, they leads to the formation of what? See here I am showing with respect to energies. 1, 2, 3 like this. Now this 2s and 2 2py's two 2p-wise will overlap with each other. They will be intermixed with each other, intermixing, and they will be forming hybridized atomic orbitals, that is 1s and 2p orbitals. So these hybridized atomic orbitals are sp2 hybrid orbitals. sp2 hybridized, 3 atomic orbitals are involving. So 1s and 2p, so therefore it is sp2 hybridized atomic orbitals. And around this boron, these 3 orbitals are going to orient in such a way that there is minimum repulsion between them. They can't orient just side by side. They will be orienting in such a way that there is minimum repulsion between the 3. Okay, in order to have minimum repulsion, they are going to be spaced with angle of 120 degrees. See, if one orbital is here, the second one will be here, the third one will be here, such that they will be having minimum repulsion and they are going to have a bond angle of 120 degrees. Right? Now, these 3 with 1 unpaired electron, these 3 sp2 hybridized orbitals of boron are now going to overlap with the unpaired electrons of fluorine. You know that fluorine will be having 1 unpaired electron in its 2pz orbital, isn't it? It is going to have 2pz orbital, right? So fluorine, if you look at fluorine, it is 1s2, 2s2, 2p5. That means this is having 1 unpaired electron in the 2pz atomic orbital. So that is going to overlap with fluorine. That is going to overlap with, this is what? 2pz of fluorine. This is going to pair up with the sp2 hybridized, one of the sp2 hybridized atomic orbital of boron. In this way, 3 fluorines are going to pair up and they are going to form, right, with a bond angle of 120 degrees, and the shape is going to be triangular shape. And in the earlier case it is linear shape. We can call this shape as what? Linear shape. Okay, let us take the example of methane. Hybridization or formation of methane. How this is going to explain? Formation of methane, CH4. Right? You know carbon. What is the atomic number of carbon? It is 6. Right? With the electronic configuration 1s2, 2s2, 2p2. One carbon is forming 4 bonds with 4 hydrogens. If you look at the atomic orbital, that is valence atomic orbitals, there are only 2 unpaired electrons. But how many unpaired electrons? How many are required here? 4 bonds are required. So what happens? It should undergo excitation. So carbon will undergo excitation. This is the first excitation. In the first excitation, what happens? One of the electron will jump into the vacant 2pz orbital and it is going to form 1s2, 2s1, 2p3, isn't it? 2p3. Now how many unpaired electrons are available? 1, 2, 3, 4. Right? So these 4 with difference in energies, they are going to intermix. Okay, this is of S subshell and these are of P subshell. So there is a difference here. So therefore what do they do? What do they undergo? They undergo hybridization. That means intermixing to form what? Hybridized atomic orbitals. How many are going to form? 4 hybridized atomic orbitals. 1, 2, 3, 4 like this. 1s and 3p orbitals are going to intermix and they are going to form sp3 hybridized atomic orbitals. Atomic orbitals are going to be formed. Now these 4 are going to arrange around the carbon in such a way that there is minimum repulsion. You know that they are going to arrange in a tetrahedral manner with 4 orbitals arranged 3-dimensionally in the space such that they face minimum repulsion. Right? So around the carbon, these 4 are going to orient. Actually, one of 2 atomic orbitals will be away from the plane. One will be above the plane, one will be below the plane. But this board is 2-dimensional board. I can't show that. So here just I am showing like this. Right. So in order to minimize the repulsion, it is going to occupy. They are going to maintain what? 109 degrees 28 minutes of bond angle with 1 unpaired electron in their valence shell. Now what happens? 4 hydrogens. You know that each hydrogen will be having only 1 electron, that too in the 1s orbital, that is also unpaired. So that hydrogen with its 1 unpaired electron it is going to overlap with these 4 hybridized orbitals and it is going to form a bond like this around the carbon. 4 covalent bonds are going to be formed around around 1 carbon atom, right, with a bond angle of 109 degrees. And the shape is what? Shape is tetrahedral shape. NH3. This is having 3 bonds, right? If you look at ammonia, this is requiring 3 unpaired electrons. But if you look at nitrogen is having 7 electrons with the configuration 1s2, 2s2, 2p, 3. So here, even though nitrogen is having unpaired electrons like this, 3 unpaired electrons which are required for bonding with 3 hydrogens, but still this will undergo intermixing. Still this is also going to undergo what? Intermixing. And after undergoing intermixing, what happens? It is going to form 4 hybridized atomic orbitals, in which one of the orbital is paired up and the 3 are unpaired. So this is what? sp3 hybridized atomic orbitals. Right? Out of these 3 sp3 hybridized, that means 4 orbitals, 1 is with lone pair, right? 3 are unpaired. Okay, 1 is lone pair, right? And the 3 are unpaired. So these are going to arrange around nitrogen such that this lone pair will be occupying more space, as we have already seen this. We have already discussed about this. Lone pair are going to occupy more space, whereas bond pair electrons are going to occupy less space, right? So therefore it is not going to occupy more space. With the remaining 3 will be forced. Actually they should be with this bond angle 109 degrees 28 minutes. But due to the presence of one lone pair in this place, what happens? The remaining 3 orbitals will be compressed. That means their angle decreases and they are going to maintain 107 degrees 48 minutes. 107 degrees 48. From 109 it has decreased to 107, right? With 1 unpaired electron. right? Now what happens? The remaining 3 hydrogens. How many hydrogens are there in ammonia? 3 hydrogens. These 3 hydrogens are going to paired up. They are going to be paired up with these 3 unpaired electrons, and they are going to form a pyramidal molecule like this. Pyramidal molecule like this. 107 degrees 48 minutes. So in this way, hybridization, the concept of hybridization is able to explain the bonding in these molecules, covalent molecules successfully with their shapes and bond strengths.